Okay, maybe we can start. So just announce again, the midterm will be this weekend. I will post the midterm exam on Canvas, hopefully by midnight of Thursday. And then you have a whole weekend to do that. The midterm exam will contain 2 problems, and you only need to choose 1 problem to do. Of course, you can also do both of them. And eventually you will be graded by your highest graded problem. That is to say, not try to punish you. Just if you want to do both of them, you can be graded by your highest one. If you are very confident that you can do the best in one of them, you can also do one. Each problem is supposed to take half an hour to finish. So at most, you will take 1 hour, but it's up to you. There's no time constraint. So you have basically 3 days to do it in the end submit by end of Sunday, okay? The homework, the midterm problem will based on all we have learned in part 1, not about part 2. So it will be very much emphasized on quantum measurements, on, for example, unitary evolutions. So basically, that's the 2 things we have learned previously. So take a look at your homework, and I think that will be very helpful. But anyway, it's open book, so don't worry too much about that. After you see the problem, you still have chance to study. So that's the idea. Okay, so we will start our lecture today. Okay, well, hello everyone. Welcome to 130B, Quantum Mechanics. Today we are going to continue our discussion of angular momentum. And we know angular momentum was introduced to describe rotations. Angular momentum operators are generators of rotations. And last time we have learned that we can label the representation group, the representation of the rotation group by spins. And the concept of spins, or this angular momentum quantum number, actually labels different spins, labels different sub-Hilbert space. For example, if you have a spin 1/2 particle, what that means is that this particle, in terms of its spin degrees of freedom, it contains 2 states. If we have a spin s particle, then it contains 2s plus 1 different states. And then one basic task is to represent our angular momentum operator in this Hilbert space. Because once we know how angular momentum operator gets represented, we automatically also know how to represent all the rotation operators. Because all the rotation is nothing, but if you raise the angular momentum, you dot product angular momentum with the angle that you want to rotate and raise to the exponent, that generates all the unitary rotations. So the only thing we need to know is how to represent angular momentum operator in each representation. That's one thing. That's what we discussed previously. And then what we discussed last time is that not only that, sometimes we are also curious about how to fuse different spins representations together. So if you have 2 spin 1/2 particle, if you want to fuse that, on the angular momentum operator level, it's very simple that the total system's angular momentum is just a sum of each subsystem's angular momentum. Of course, here the angular momentum operator need to be considered as a joint action or as extended to the total system, meaning that you need to first, for example, for this SA, you need to first represent it as a 2x2 matrix on the A particle, also tensor the identity matrix on the B particle, such that it represents the angular momentum operator on the whole system. And the whole and the total angular momentum is just a sum of these 2 operators. So following those principles, we can, in principle, write down representations for total angular momentum and also for each one of them, and also for the total angular momentum as matrices. And by diagonalizing these matrices, we found that this total angular momentum can split, its representation splits. The reason that it must split is that previously, by quantum bootstrap, we already know that the only feasible representation space for this angular momentum is just labeled by so-called J and M quantum number, or this S and M quantum number. So if you have a space on which you can represent this angular momentum operator, but if it does not belong to those irreducible subspace, then there must be a way to split it. And then the way to split it is to look at the eigenvalues of this S-square operator, because S-square operator's eigenvalue associated with the S quantum number, or maybe J-square operator, its eigenvalue associated with the J quantum number. And that J quantum number, different J quantum number labels different subspace. And previously we learned that the way to combine these angular momentum is to go through these projection channels. There are two different possibilities when you fuse two spin 1/2 particles, and then each fusion channel corresponds to a projection matrix or a projection tensor. And that projection tensor is also called fusion tensor. Last time we have learned the fusion rules. Fusion rules basically tells us if you fuse two spin J1, or let's say angular momentum J1 and J2, two particles together, what are the possible outcome angular momentums? All the outcome angular momentums are the direct sum of all these possibilities. These possibilities just starting from the difference between these J1 and J2, all the way to the sum of J1 and J2, and then each time add 1 to the minimum, basically, until you reach the maximum. Okay, so that's the rule. Of course, if there's no difference between minimum and maximum, all the intermediate term will vanish. This is just, you should treat that as a for loop, that it starts from the starting value, end up with the ending value, with the increment of 1, basically. That's the fusion rule of how to fuse two spins together. For example, following this fusion rule, although previously by matrix diagonalization you can already find this rule, but using this fusion rule you don't need to go through any matrix diagonalization. You immediately infer from these quantum numbers that what are the possible outcomes. And then each fusion channel, meaning that each like 1/2 goes to 0 or 1/2 go to 1, they correspond to a fusion tensor or matrix like that. And the matrix elements are the Clebsch-Gordan coefficient. So for these coefficients, you can either look it up in Mathematica. In Mathematica, what people usually type is the J1 and M1, J2, M2, and J and M. So if you want to know the fusion channel from spin 1/2 and spin 1/2 fused to spin 1, and then within that fusion channel, you particularly want to know the CG coefficient that is associated with M1 equals 1 minus 1/2, M2 equals 1/2, and the outcome M3 equals 0, so, or maybe called M equals 0, then you can type all this into Mathematica, and there's a function that basically computes this coefficient for you. So that's one way to infer these numbers. Okay, so last time I think I explained how to view this fusion channel as a tensor. This tensor basically describes how you recombine the basis of these two spin 1/2 into the basis that is in the spin 1 subspace. So that's why it is a 3×4 tensor, and 3 correspond to the number of states in spin 1, and 4 correspond to the number of states in spin 1/2 tensor spin 1/2, which is 2 times 2 equals 4, okay? So sometimes we can also draw pictures like this in order to visualize the way that we split the spins. For example, we can say that I want to compute this fusion channel pi. The way to do that is to first construct the total angular momentum operator for both of the systems. Suppose I have two particles, one carries spin J1, the other carries spin J2. This diagram basically corresponds to the matrix representation of the total angular momentum squared. So the matrix will be labeled by the row index, which is labeled by M1 and M2. When I draw J1 here, I implicitly mean that on this leg, you can basically put M1 indices. On this leg, you can put M2 indices, such that M1 indices ranging from minus J1 to J1, and M2 indices ranging from minus J2 to J2. So by previous Previously, we have already learned how to represent angular momentum operators and how to tensor them together and how to construct the total angular momentum operator as matrices. So you should really think of it, although it looks like also you can either think of it as a 4-leg tensor or you can think of it as a 2-leg matrix, because you can basically group these 2 legs together or these 2 indices together and these 2 indices together and call it the row index and column index of a matrix. And then by matrix diagonalization, we mean that we need to find a unitary transformation such that it transforms this matrix into U dagger and then the diagonal matrix and then U, right? So that's what matrix diagonalization or finding eigenvalue, eigenvectors are doing. So by doing this, we can basically split this matrix apart between its row index and column index and rewrite it in this way. By rewriting the matrix in this way, you automatically find all the different eigenvalues, which is encoded in this diagonal matrix, which we usually draw as a square. And then because this matrix is diagonal, then this green line basically is the index here and the index there is the same. And then this pi as a unitary transformation or as the basis vector that or the eigenvector by diagonalizing this matrix automatically emerge as the CG coefficient, as the fusion tensor, okay? So this formula basically tells us at a high level how this fusion tensor were constructed. So this is a very general formula that whenever you have 2 spins, J1 and J2, you can always first construct the total angular momentum operator in the tensor product state, diagonalize this operator as a matrix, and group the eigenvectors by their eigenvalues within each degenerate eigenvalue subspace. And the eigenvalue will correspond to the J3 value in this way. The eigenvalue, no matter what it is, it will correspond to J3 times J3 plus 1. And the degeneracy will automatically be 2J3 plus 1. Although this is not obvious that this eigenvalue will appear this amount of times, but if you follow all the process, all the steps correctly, by mathematics, angular momentum as a SU2 Lie group, it must have this kind of representation. So it is a mathematical conclusion that this eigenvalue will appear this amount of times when you try to diagonalize this matrix. So this basically infers basically from that, you can infer what's the spin quantum number in that block. Then you collect all the eigenvalues all the eigenvectors correspond to this eigenvalue. And those eigenvectors basically correspond to the unitary transformation you have to perform on the basis. They form the fusion vertex. They tell you what kind of basis transformation you need to perform in order to transform from this product state, space to the specific resulting fusion outcome subspace. Okay. For example, here is if you don't know how to do that, here is an example like. For example, in the previous one, we calculate spin 1/2, and fuse to spin 0 or spin 1. But we know that spin 1/2 and spin 1 can also fuse, for example, into spin 1/2 and spin 1/2 and spin 1. You can fuse to spin 1/2, spin 3/2. The reason to see that it's correct is because spin 1/2 has 2 states. Spin 1 has 3 states, this has 2 states, and then this has 4 states. So 2 times 3 equals 2 plus 4. So you can ensure yourself that things are correct. Okay, so for example, we wish to find the fusion vertex associated with a spin 1/2 and a spin 1 and fuse to a spin 1/2, which is taking the first channel. And then that channel, you can immediately see that the fusion, the result should be a 2x6 matrix. So in the end, we want to get a 2x6 matrix. So let's see how we can possibly do that. First, we form the total angular momentum operator in the space. I think maybe let's not go to the detail, but there are ways. If you look at those codes, remember you can click on the side and then review this code. Maybe it's too difficult, but if you take a look, you will learn how to write it in Mathematica if you're curious. But in the end, those are not important. You can follow the code there and then compute J square. Coding is not the important thing I want to teach. I just want to tell you how to, you just need to follow what we have described previously in the lecture notes. And then you can use whatever language to code, Python or Mathematica or MATLAB, whatever. But in the end, the first step is to first construct J square operator. And then we can see J square operator must be a 6 by 6 matrix, right? Because it's first represented in this product Hilbert space. And this is the 6 by 6 matrix. And you need to first construct that. And then you need to find the eigenvalues of J square. And then if you perform a matrix diagonalization, you will automatically find these eigenvalues. And these eigenvalues will automatically arrange into two parts. One is the eigenvalue 3 over 4, the other is 15 over 4. And this guy has twofold degeneracy, this has fourfold degeneracy. The twofold degeneracy one is here, fourfold degeneracy one is here. So the twofold degeneracy one corresponds to spin 1/2, and this corresponds to spin 3/2. So you know that the eigenvector associated with this eigenvalue should correspond to the eigenvectors that linear combine my original basis into spin 1/2. So that's why you can aggregate or you can collect all the eigenvector or group all the eigenvector according to their eigenvalues. So here I'm writing eigenvector as row vectors. So each row is an eigenvector in this representation, and then I'm grouping them in terms of their eigenvalues. For example, spin 3/4, this is spin 1/2, which corresponds to eigenvalue 3/4, has these two eigenvectors. And these two eigenvectors put together are indeed the fusion channels we're looking for. You can check the representation of this J3 in this spin 1/2 subspace and find this kind of J3. It's not guaranteed that this basis vector will automatically arrange in the normal order, so sometimes you need to reorder the lines in different rows such that it fits the convention, our convention that when we represent J3, it should look like a Pauli Z matrix. Here it looks like a minus Z matrix, so that's why you need to reorder these two lines. But anyway, this is how we compute these fusion tensors. Okay, any questions? So here comes homework 3. Homework 3 is trying to provide you an opportunity to exercise all we have been talking about so far. And the homework 3 is indeed a problem of consider a spin 1 particle, which is like this, and spin 1/2 particle, which is B, if particle is like that. And then we try to first write down the Hamiltonian as a matrix, and then you will know it's a 6 by 6 matrix. It's trying to do the same thing as exercise 23. And then if you don't know how to write down SA and SB separately, you can look at the previous exercise. I think we have exercise 21, which teach you how to write down SA and SB separately. Exercise 22, which teach you how to write down their dot product. And then exercise 23 is a more specific example, which exactly has the same setup as the homework. So you can look at all these exercises and try to finish the homework. The requirement is that you write down the 6 by 6 matrix representation of H and find the eigenvalues of this matrix. I don't recommend you to do it by hand. It will be too tedious. So it is better either you use any mathematical software or Mathematica to find the eigenvalues. And as I said, you will automatically find the eigenvalues that has a twofold degeneracy and fourfold degeneracy. And then based on that, you can try to split, you can collect the eigenvectors and then construct the projection operator or the fusion tensors, which projects spin 1/2 tensor spin 1 into the spin 1/2 subspace or into the spin 3/2 subspace. And then this is the fusion tensor, and then I keep saying projection operator. The true projection operator is actually given by this tensor, which is a 2 by 6 matrix. This Hermitian conjugate of this guy is a 6 by 2 matrix. So if you have a 6 by 2 matrix multiply a 2 by 6 matrix, the resulting matrix, this P1/2, is a 6 by 6 matrix. For the same reason, this is also a 6 by 6 matrix. So try to write those 6 by 6 matrix down, and then you can show that magically these matrices, although we go through all these process to construct this matrix, it seems that it requires us to do matrix diagonalization, find the eigenvector, and use eigenvector to do some calculation. But eventually, it actually has a simple expression. This expression is you can rewrite this matrix in terms of this SA.SB. How do we show that? Well, we just take SA.SB matrix and then minus identity over 2 and then put all the coefficients together, and then you should be able to show at the matrix level, the resulting 6 by 6 matrix here is the same 6 by 6 matrix as P1/2. This is very similar to the previous thing that we have learned, that if you have a spin 1/2 system, like a qubit, right? Previously we learned that you have n dot sigma equals +1, this state. This state has a projection operator, which is like this state. You do a cat and bra. This is the projection operator, project to n dot sigma equals +1. And this has a very simple expression, which is this n dot sigma over 2. I think that's in your previous homework. So the similar thing will happen again here. So this is for spin 1/2. This is for something more complex. For example, for spin 3/2 for any spin j, basically we can perform this kind of projections, and this projection operator magically also have simple analytic expressions. But if you are clever enough, you should be able to actually derive this on the algebraic level. You can think about it, how to prove that in the algebraic level without explicitly computing the 6 by 6 matrix here and 6 by 6 matrix here. Either way should be fine. If you can prove that directly, that would be great as well. Okay, so that's homework 3. Yeah. But it's always good to start from some very explicit calculation and see by your eyes that this 6 by 6 matrix magically coming from 2 very different approaches matches exactly, and then that will motivate you maybe to think deeper. Why? What's the reason behind that? Okay. So this is what I want to talk about, the fusion tensors. Fusion tensor basically is a bunch of data. You can think of fusion tensor as an array of numbers, and all these numbers basically describe the process of fusing spin 1/2 and spin 1, of fusing J1 and J2 particles into a J angular momentum or quantum number, spin J particle. Okay, so from that on, maybe we can think of things more abstractly. So that's what I want to continue talking about. The last thing about angular momentum, which is called F symbols. It's a very important concept because we have already learned that if you have J1 and J2, you can fuse into, for example, J4, and then you can further fuse J4 and J3 into J6. The idea is that we already learned that how to represent our spin operator in each representation. For example, J1. We also learn how to do basis transformation that fuse J1 and J2 into J. Then you may wonder that this is a single line, this is 2 lines, how to merge into a single line. Maybe I have 3 lines, how to merge into a single line. Maybe I have 4 lines, how to merge into a single line, right? So the idea is that not only we want to know how to represent spin operator in a single representation, we also want to know how to represent it in 2 spin representations, 3 or 4 or more of them. So in order to solve all those problems, we need to know how does 2 spins fuse to a single spin, what are the possible fusion. And that has been discussed previously that it corresponds to a fusion vertex whose coefficient are CG coefficient. But then people will be worrying about what about higher, more spins? Do we need to do this kind of exercise for each one of these cases? And then it will be endless number of calculations. So that's why F symbol is important, because F symbol tells you enough. You only need to know what is the single fusion. You only need to know what is a fusion between two spins. You can automatically construct the fusion tensor. There's also a fusion tensor here for 3 spins, because any fusion of 3 spins together can be considered as a 2-step process. You first fuse the first 2 together, and then fuse the, so it's like J1 fused with J2, fused with J3. You can either think you first fuse the first 2 together and fuse with J3. Or you can think there's another way of doing that. You can first fuse the last 2 together and then fuse the first one, right? So there are 2 different ways of fusing J1, J2, J3 together finally into something called J6. So you can either do the first 2 together and then fuse with the third one. And here what you need to use is the 2-spin fusion, the fusion vertex there. And here you also need to use the 2-spin fusion. You just need to use it twice. But then it comes a problem, because it seems that there are 2 different approaches to fuse 3 spins together. If you fuse 2 spins together, there's no ambiguity. But if you fuse 3 spins together, there's an associativity problem. You need to worry about whether this fusion is associative. For number product together, we are all so familiar with that. We know that the multiplication of number is associative, meaning that if you have ABC, 3 numbers you want to multiply, you can multiply the first 2 together, multiply the last 2 together, no problem with that. But these are spins, and these are Hilbert space representations. It may not be the case. So these F symbols basically describe actually, they are not equivalent. But they are not equivalent, but they are related by transformations. They are equivalent up to certain transformation, and that transformation is described by F symbol. So in order to be more explicit, so let's first study this way of fusion, and then let's try to construct what is the fusion tensor in this case. And then we will study another case, and then we will compare them. And by comparison, we will be able to figure out what I'm going to talk about, hopefully. So here I will use examples to describe how to fuse, for example, J1, J2, J3 are both spin 1/2. And then if all of them are spin 1/2, so spin 1/2 fused with spin 1/2 fused with spin 1/2. If you fuse the first 2 together, what are the possible outcomes? It's 0 plus 1, right? Fused with spin 1/2. And this direct sum and direct product notation has the same idea as distribution rules, that you can distribute it. It becomes 0 plus tensor spin 1/2 plus 1 tensor spin 1/2. It just works as a multiplication and addition, the same thing. So 0 fused with spin 1/2, there's only one possibility, that's spin 1/2. And then this 1 fused with spin 1/2 has 2 possibilities, spin 1/2 and spin 3/2. So you can see, if I fuse 3 spin 1/2 together, I can altogether get 3 subspace. 2 of them are spin 1/2, and they are actually different. And then the final one is spin 3/2. And then if you count the space dimension, this is like 2 times 2 times 2, which is an 8-dimensional space in total. This is 2 plus 2 plus 4, which is also 8 dimension in total. So the dimension matches, okay? So that's the result we expect to get. But if I want to say, let's just fuse 3 spin 1/2 into a spin 1/2, then there is some ambiguity, because I haven't specified I'm going to fuse them into which of these spin 1/2s, right? So actually, this fusion channel is not unique. It is because of that non-uniqueness that there is some ambiguity. And then this ambiguity leads to the leads to the inequivalence between these two different ways of calculations. But these two different ways of calculation will eventually only be related by a basis transformation again. So that's what I want to explain. So okay, now let's look at this example. From this example, you can see if I want to fuse them together, I can either, in order to obtain this spin 1/2, I need to first fuse them to the spin 0 channel and continue. In order to obtain the second spin 1/2, I need to fuse the first two into the spin 1 channel and then continue, right? That's what we see here. So we can either fuse, so that's why this J4 basically labels. If you first fuse them to the spin 0 channel and then fuse with spin 1/2, you get spin 1/2. Or you can fuse them into the spin 1 channel. It's still possible to fuse another spin 1/2 and get spin 1/2 again. So there are two different ways. The first way is to fuse with the first fuse into the spin 0 sector. So that corresponds to you first take spin 1/2 and spin 1/2 and fuse to spin 0. And then during this process, when the first two spins are getting fused into spin 0, the third spin, this is the third spin. The third spin is not changing, so it corresponds to an identity matrix, although I also denote it as a pi, as a fusion channel, but it actually corresponds to a 2x2 identity matrix, which basically means J3 doesn't change through this process. Okay, so we are at this time step. Now we are at this time step, what we need to do is we take a spin 0 and spin 1/2 and further fuse it into spin 1/2, which is this matrix. So we need to first apply this operator and then apply this operator, right? If we want to do two things to our basis, we need to do the first thing and then followed by the second thing. Then that in the operator level, that means we need to first apply this matrix and multiply with that matrix. So following the previous discussions, we know how to construct all these fusion vertices, and then we will be able to follow all the algebras. And then if you don't know, look at exercise 24, and there were the details there. And then you can obtain these final fusion outcomes, which we denote as alpha 0. And this fusion tensor basically is a 2 by 8 matrix. This 2 by 8 matrix means that if I start from this 8-dimensional Hilbert space, which I have 8 states here, and then I want to fuse into one of these spin 1/2, for example, the first one. So I want you to tell me how I should recombine all these 8 basis states that I start with in such a way that I obtain the 2 basis states, which exactly correspond to the 2 possible states in this spin 1/2 subspace. And this matrix, this 2 by 8 matrix, exactly describe the construction. You need to combine all these 8 different bases in such a way with all these coefficients in order to create a spin 1/2 upspin, and then this is the wave function for the downspin. Okay, so that's the meaning of this result. Of course, we can also choose J4 to be 1, which is this intermediate step. The first two spin 1/2 can either fuse to spin 0 or spin 1, but if you choose spin 1, you go to the other spin 1/2 result. And then for that case, you go through the same algebra. And then it's a little bit complicated, but the result is like that. And then that's it. That's another way of fusing 3 spin 1/2 into a single spin 1/2. So we can see, depending on the choice of J4, which is the spin in the intermediate line. Maybe let me draw the picture here. I have spin 1/2, spin 1/2, spin 1/2. And then I want to fuse to spin 1/2. I can choose J4. This is my J4 can equal to 0 or 1. But there's another way of doing that. It's like this. Spin 1/2, spin 1/2, spin 1/2, fuse to spin 1/2. Here, there's also an intermediate line, J5. It can also be 0 and 1. That's what I want to discuss in the following, which means there's another way of doing it. For the first way, there are 2 fusion tensors we already compute as this alpha equals okay, as I denoted as alpha 0 and alpha 1. Alpha 0 means this 2 by 8 matrix. Alpha 1 means this 2 by 8 matrix, okay? And then I do the same exercise for this fusion. And for this fusion, what you need to do, for example, I choose J5 to 0. Then the first thing is that J1 during the first process doesn't change. So this spin 1/2 corresponds to J1. J1 never gets changed in the first step. So it's an identity channel. But what happens to J2 and J3? J2 and J3 fuse to 0. So that's why I need to tensor this J1 with this J2 and J3 fusion together in this order. And then this will end up with a spin 1/2 tensor spin 0. So now I need to further take this spin 1/2 and this spin 0, tensor them together and fuse them into the final spin 1/2 of J6. So this is J5 actually here. So you just need to compute all these pi tensors or matrices and use this tensor product and matrix multiplication, and then you go through all this linear algebra and obtain a matrix like that. This matrix describes how I should recombine all the 8 basis states of this 3 spin 1/2 in a way that can construct the spin 1/2 result in this J6, given that J5 is going through the 0 channel, okay? So this 2 by 8 matrix is another linear combination of the 8 bases to construct a spin 1/2, which we call the beta 0, in order to be different from alpha 0, okay? And then for J5 equals 1, there's another beta 1. It's the same idea. It's just going through the computation again. So if we summarize all these matrices together, we can see we have here, by choosing J4 equals 0 and 1, we have 2 fusion matrix, which is alpha 0, alpha 1. I just use these 2 symbols to denote the 2 by 8 matrix. For here, we get beta 0 and beta 1. So this corresponds to the 2 different ways of getting spin 1/2. These 2 correspond to another 2 different ways, which is not written here, because all this calculation is assuming that I'm fusing the first 2 spins together. But if you are fusing the last 2 spins together, you need to go through this calculation again. Then you will find another 2 spin 1/2. And interestingly, all these spin 1/2, although they are all spin 1/2, they are all different. If you take a look at let's go through this alpha 0. Obviously, alpha 0 and alpha 1 are different, right? Because the numbers, just by looking at the numbers, they're not even the same. But even alpha 0, you can see, it starts from 2, 0, and then square root 1 over square root, and then a 0 minus 1 over square root, something like that, right? If you look at beta 0, which looks very similar, but it's not the same, right? Immediately, it doesn't arrange this 1 over square root 2 in the same way. So beta 0 is also not the same as alpha 0 or alpha 1. It's also not the same as beta 1. So all these 4 matrices, each of them are 2 by 8 matrix. They are all different. But if they are all different, that means, well, if I try to fuse the first 2 spins together, I get alpha 0 and alpha 1, two possible answers. And then fusing the last 2 spins together, I also get 2 answers. And then it seems that there's not an inequality between these 2 different ways of fusion. That makes mathematicians and physicists very annoyed at the beginning, because it's like our fundamental belief breaks down. We believe that our universe is associative, because if you combine particles together, it should not matter in which order you combine them. They end up with the same space. So then someone discovered that, wait a moment. Although these matrices, as a 2 by 8 matrix, they all look different, but there is actually a relation that is connecting them. And that relationship is called F symbol. That's why people, this F has no meaning. It is just because in the literature, people use this symbol F to denote this coefficient. Sometimes it's also called F matrix or 6J symbol, Wigner 6J symbol. and things like that. But by definition, it just means this F symbol, you can see, it depends on 6 different J's, which is crazy. But the reason is obvious, because it first needs to depend on all the input spins. So F symbol is describing how to fuse 3 spins together, right? If you want to fuse, because we already know how to fuse 2 spins together, it's already here. The new question is here, how to fuse 3 spins together. The way to fuse 3 spins together, you need to start telling me which 3 spins are you going to fuse together. And then you also need to specify the fusion outcome such that I know what is the explicit fusion channel you are talking about. But given that it is not, it does not fully determine this fusion tree, because this fusion tree can either go this way or go that way. And by going this way and that way, there's an intermediate spin, which is either J4 or J5 that is emerging. So there must be a relation to convert this fusion tree to that fusion tree, meaning that whatever result you obtain, whatever fusion vertex you obtain in this construction here, which is labeled by J5 equals 0 or J5 equals 1, there are 2 different possibilities. So these 2 different possibilities should be recombined into the 2 different possibilities labeled by J4 equals 0 or J4 equals 1. And this recombination is again a unitary transformation. So even this channel, it is already beyond the state. Previously, we are talking about states. We can perform unitary transformation and combine them. This channel looks like a quantum process, like a time evolution process or the projection process. And this process, quantum process, can also be linear combined. And then by saying that these 2 different ways of fusing the 3 spins are consistent with each other, we don't mean that alpha 0 equals beta 0, alpha 1 equals beta 1, because really they originate from very different ways, very different intermediate steps of fusion, so we should not expect them to be identical. But although they are not identical, they belong to the same space. They describe the same space of quantum processes, which spans a 2-dimensional space, which means there are only two possible process that fuse 3 spin 1/2 into a single spin 1/2. And no matter how you choose the fusion tree, you are just choosing different bases in these total possibilities of fusion processes. And for example, if you choose this one and this one, they will be related by a unitary transformation. And this unitary transformation, in terms of the fusion tree, is called F matrix or F symbol. It is a unitary transformation. And then because this symbol, if you consider each matrix element, for example, this specific element will correspond to J1, J2, J3, J6, all equals to spin 1/2. And then J4 equals spin 0, and J5 equals spin 1. So it will be 1/2, 1/2, 1/2, 1/2, 1, 0, and 1, okay? So you can see this matrix element minus square root 3 over 2 is actually specified by 6 different J. So that's why it's called 6J symbol in the literature. More rigorously, 6J symbol refers to something like that, and then the F symbol is actually 1-to-1 related to 6J symbol by some expressions. But never mind, it's just because when humans create all these notations in the history, there's some inconsistent convention. This F symbol is more used in mathematics, and this 6J symbol is more used in physics. And it's very unfortunate that these 2 groups of people don't communicate well enough that they create 2 different symbols. But in the end, they are just equivalent. They are just 1-to-1 correspond to each other. And Mathematica also provides a way to compute 6J symbols, which is, don't worry about that too much. It's, I just want to tell you all these numbers people know how to compute in principle, okay? So this F matrix or F symbol tells us now you don't need to worry that as long as you know how to fuse 2 spins together, you also know how to fuse 3 spins together. Although fusing 3 spins together has 2 different fusion trees. It seems that at the first glance, the result is not the same, but their results are consistent to each other in the sense that the results are related by transformation. which is given by the F symbols. So now mathematicians are not satisfied by that, because when they want to prove something, they actually want to prove it all the way to infinite number of spins. So they say, okay, for 3 spins fusion into a single spin, now we know that you can fuse it in different ways, but don't worry, they are consistent. They are related by F symbols. So the crazy mathematicians go further and fuse 4 spins together. They want to understand how to fuse 4 spins together into that spin. But in that case, there are even more ways of fusing them together. For example, if I have 4 spins, J1 all the way to J4, I want to fuse into the outcome J5. I can either fuse the first 2 together and then combine with J3 and then combine with J4. I think this diagram is very intuitive. Just by reading this diagram, you know what I am talking about. So first of all, you can first perform a F symbol. You can perform a so-called F move here. Because, yeah, maybe let's not talk about F move. Let's just say that actually there are actually 5 different ways of fusing 4 spins into a single spin. So unlike 3 spins into a spin, there are only 2 different ways of association. But if you have 4 objects you want to fuse into a single J5, there are 5 different ways of associating them. So the associativity leads to 5 different diagrams. That is 5 different possible orders that you can fuse things together. For example, first fuse these middle 2 together and fuse with J1 and fuse with J4 and so on. And these 5 different ways of fusing them are related by the basic process of F move. Because F move, or F symbol, the reason that people call it F move is because it provides a unitary transformation that allows you to transform any diagram that looks like this to a diagram that looks like that. Okay? So that corresponds to you are taking the middle leg, this middle line. You're taking this middle line and moving through these vertex and then bending it to the other side, right? So this is a F move. For example, if you start from this fusion tree, you can perform a F move or this F transformation here. You can start from this part that's labeled by this and this vertex. You can take this J3 and you can slide the J3 through this vertex to the other side, to here, and then that gives you this fusion tree. And starting from this fusion tree, you can take the J2 line. You can take the J2 line and slide through there and then end up with here. So you can first perform a F transformation for these spins and then perform a F transformation for these spins, and then you end up with this fusion tree. Or another way of doing this, you can first take the J2 line and then sliding it through this vertex and to here that goes to this fusion tree. And then with this fusion tree, now you take the J10, which is an intermediate line. You can also slide it through, and then it goes to this fusion tree. And for this fusion tree, you take J3 and then slide it through this vertex, and then you get this fusion tree. So you can go through another 3 different F transformations and end up with the same fusion tree. So now mathematicians ask the question whether these 2 different ways are also consistent. You can start from this fusion tree and go there, or start from this and go there, whether they are consistent. If they are not equivalent, maybe there's another, there will be another basis transformation that is required in order to take you from the upper branch to the lower branch. And that will be a nightmare. And fortunately, that is what mathematicians has verified, that all these tedious basis transformation stops at this level, that it turns out that the upper branch and the lower branch transformation give you precisely the same answer, which means that this truncation this discussion truncate at this order. As long as you know how to fuse 2 of them, and fusing 3 of them, you need to know that there is an F symbol, they are not equivalent. But if you want to fuse 4 of them, then you can just use the same F symbol to take you from any fusion tree to any other fusion tree, and the whole mathematical system is consistent in the sense that 2 different ways of connecting the fusion tree will end up with the same result. And this equation is called the pentagon equation. The reason it's called pentagon, I think, it's obvious, because if you look from far, this 5 diagram forms a pentagon. And then the mathematicians prove a theorem that guarantees that pentagon relations are always satisfied. So everything gets ended here, that you only need to know all the CG coefficients. So the CG coefficient basically specify the fusion vertex, and the 6J symbol or the F symbol specify how you connect different 3-way fusions. And there's no further symbols or coefficient you need to memorize, because all the later higher spin fusion will all be consistent. So with that, thanks for your attention. Yeah.